So hello everyone. So we are going to cover the control phase of Six Sigma. Okay. So control phase of Six Sigma is very important because now we have already improved the current state where we have improved the project metric that we started it in the define phase, the goal statement that we come up with in the define phase. So that has already been accomplished in the improve phase. Now we are trying to get into the control phase to ensure that all the solutions that we've implemented are in control now. Okay, so this is a very important phase of Six Sigma, wherein we try and see that whether the process that we have designed, the new process that we have designed, is in control or not. And if it's not in control, what are the things that we're going to do to make it in control? So that is the whole objective of doing the control phase. Okay, so let's start and let's get into it. So as I said, control phase is the last phase in DMAC cycle of Six Sigma. It's about sustaining an improvement which has been done. Sustained improvement once a new solution is implemented. This is also referred as holding the gains. And this is proactively monitor the process on an ongoing basis. So we are proactively monitoring the process. So since we haven't completed the project, but we want to ensure that the process is in control, and that's the reason we are proactively monitoring it. It is transitioning from project to process, because earlier it was a project which is for a limited point in time, and now we are transitioning into a process that it will become a business as usual once once this is being transitioned. So to get into it, in control phase, there is a very important subject that we cover, which is called control charts. Just to tell you the background of control charts, that control charts was developed by Dr. Walter Andrew Short in the year 1920. Control chart is just like a run chart, which includes statistically generated upper and lower control limit. Okay, so we'll understand this better, that what is the meaning of upper control limit and lower control limit. And before we understand the upper control limit and lower control limit, let's understand the different sort of variations that we have. So we know the common cause, which is inherent to the process or random and not controllable if only common cause present. The process is considered stable or in control. So common cause variation is a kind of variation which is there in almost all the processes, which is sometimes not controllable, and it is a common cause which seems that the process is in control, because every process that you look at, be it manufacturing process, be it service, be it finance, HR, healthcare, telecom, you find some amount of variation in it. Some bit of variation is already there. Okay, so that's the inherent variation which is there in any of the process. And if that sort of variation is there, we would say that the process is in control. Okay. Then there is another type of variation which is known as assignable cause or special cause. This is this sort of variation. If there is in the process, it seems or says that this process is not in control. This is outside the control. So variation due to outside influences, if present, the process is out of control. So like any situation, any environmental control, due to some weather, due to some natural calamities, due to any natural pandemic, that is the reason. That's sort of a special cause. Special cause is very easy to detect. It is not that difficult to detect the special cause variation. Special cause variation is kind of very easy to track, very easy to detect. However, it is very important to track. Okay. Now let's understand that what is the difference between control limit and the specification. Okay, specification limits are defined by the customer. Okay, wherein we know that it is the upper specification limit and the lower specification limit, which is being defined by the customer itself, wherein the customer says that I want these services between let's say 15 centimeter to 20 centimeter. I want the product to be between 15 centimeter to 20 centimeter. I want the quality to be between 90% to 95% or 100%. Okay, so that's the upper control limit and that's the lower control limit. That is defined by the customer. Okay. However, in control chart, what we need to know is the control limit. Control limit is something which is defined by the data itself, which is not defined by the customer. So when we prepare control charts, you would see that there are control limits already there. So that is what is referred to as control limit. So specification limits are defined by the customer. However, control limits are derived by the data itself. So let's get into the control charts and different type of control charts. Control charts are basically depends upon the type of data that we are working on. Okay, so there are different sort of control charts for discrete data, and there are different sort of control charts for the continuous data. Okay, so control charts, when we talk about, we consider variable and attribute. So variable is also referred as continuous and attribute is referred as discrete. So under variable, we have different variants. So if we have one subgroup, then we go for an IMR chart, which is called individual moving range chart. Okay. However, if the subgroup size we're considering 2 to 5, then in that case we use X bar R chart. Under variable chart only, if the subgroup size is between 5 to 9, we go for X bar S chart. So this is the control charts that we are going to use for the continuous data. So we are going to do a mini tab demonstration in a while. But just for now, just remember that these are the different types of control charts that we use in the continuous data. IMR, X bar R, and X bar S. Okay. So we'll talk about what is R and what is S when we do the mini tab demonstration. In the discrete data side of the world, we use different control charts. So that is dependent on whether the data size that I have is defective or defect. If it's defective, then there are two variants. If it's constant or non-constant. If it is constant, then I use an NP chart. If it's non-constant, I will use a P chart. Similarly, in a defect side of the world, when I have a constant data size, constant volume which is being tracked, then I use a C chart. And when I have non-constant under defect, I will use a U chart. So these different types of control charts are being used in projects, sometimes outside the projects. And the intent of designing this control chart is to see whether my process is within control or not. If my process is within control, which means that there is no special cause variation there in the data, which means that my process can run successfully even after the completion of this project. However, if there is a special cause variation in the data, which means if there is, which means the process is outside control, then in that particular case, it is very, very important to look at what are those special cause variations and try to figure out. So when we do a mini tab demonstration, we will be able to show you that how do we identify whether the process is outside the control limit or not, and how do we say it's a special cause variation. So we'll show you the mini tab demonstration of all these control charts, and then you will be able to understand.